So a Lagrange multiplier problem with two constraints. This is similar to number 27 in your homework. So and I'm kind of excited. My videos yesterday reached over 1,000 views on YouTube.
Wow, nice. That is so impressive.
Yeah. What's that? I can sign up to monetize, but I'm not sure how that would work with district policy. So
The
and
district does not know.
and I'm still a probationary teacher, so try to do things above board. So on this problem, we want to find the highest point on the intersection of, we have a cone x squared plus y squared minus z squared equals 0. And the plane x plus 2z equals 4. So if we're the cone, this equation and this equation are our constraints. So each of those are constraints. If we're looking for the highest point, what function are we trying to maximize? If we have, so just, so the what variable in our three-dimensional coordinate system gives us the height if we're z? So all we're trying to maximize f of x, y, z equals z. We're just trying to maximize the height, how far it is above the xy plane. So we're maximizing z subject to these two constraints. So it has to be on the intersection of these two, of the cone and the plane. So those are our constraints, and this is our objective function. So we're going to, this is a constraint, and this is a constraint. So this is our objective function, our two constraints. So we set up our Lagrange multipliers. So del f is just going to be k. And we'll call this one, I'm going to call this function g. And call this constraint h. So del g is 2xi plus 2y j minus 2zk, and del h is I minus 2zk. And our Lagrange multiplier, 2k. There we go. And it is plus. I was doing what Scotty did on the last problem. I was looking at this and brought that down. All right, and our Lagrange multiplier condition says that del f equals lambda del g plus mu del h. So we're going to set these equal to each other, and we're going to just equate components. We're going to equate the x component, the y component, and j component. So when I equate my components, I'm not going to write this all out. We're just going to equate components from here. When we equate components, I get 0 equals 2 lambda x plus 2 mu. I get 0 equals 2 lambda y. So this tells us right away that y equals 0. And I get 1 equals minus 2 lambda z plus 2 mu. And we also know that we have to have that x squared plus y squared minus z squared equals 0. And x, from our equation of our plane, x equals 4 minus 2z. So these are multiplier conditions, our Lagrange multiplier conditions, and these are our constraints. So I'm going to plug, we know that y equals 0. I'm going to plug this into this equation for x here. So we have just an equation in z. So I get 4 minus 2z squared plus, or I'm sorry, minus z squared equals 0. And when I solve that, I get z equals 4/3, or z equals 4. And we're trying to maximize z. So we look at this, the maximum height is z equals 4. Is the maximum height. And our point is going to be at -4, 0, 4.
And you get that just by plugging in your z value?
Right, so we know y is 0, we know z is 4, so we can plug in, we could solve this one for x, right? And I made a picture of this. So let me get to that. I'm getting better at doing these 3D shapes in Mathematica.
Okay, what is a saddle point? Like, I'd like to have.
I'll show. We had a picture of a saddle point yesterday. So let me, and that's.
Well, like, I know what it looks like, but why? Like, I just don't get it. How come it isn't a minimum?
Because if you're going this, so here's our saddle point. Right here in the middle.
Right.
If we're going this way, it's a minimum, but if we're going this way, it's a maximum. So it's a maximum and a minimum at the same time.
Okay.
So that's what makes it a saddle point.
All right.
Okay? All right. And then this is our constraint problem. So this is the cone, this is the plane, and we can kind of see the intersection here. And it's actually kind of elliptical because it's slanted. And then our highest point is over here at z equals 4. So that's the problem that we just did.
Let's try and make a really cool 3D shape. Like a dollar sign.
A dollar sign?
Can we do that? Let's try and figure out the equations. Or how about you do it
And we do it and then then I'll do it and show it to you. All right. All right. Any questions?
No.
Okay. So.
27.